No, it is not ninth in the periodic table of the elements. There, according to the scientists' arrangement of increasing atomic numbers, Ti is listed as 22. Yet, in terms of the estimated quantities of elements that make the Earth's 10-mile thick crust, titanium is ninth in distribution. First comes oxygen, followed by silicon, aluminum, iron, calcium, sodium, potassium, magnesium. Ninth is titanium. The first 8 together are figured to account for more than 98% of the weight of the Earth's crust. Of the remainder, there is estimated, for instance, a great deal more titanium than familiar elements like zinc, copper, tin, and lead. 2 reasons for titanium's relative abundance are that it occurs in minute quantities in many widely scattered rocks. And it is always found combined with oxygen, the most prevalent of all elements. Titanium and oxygen, in the ratio of 1 atom of titanium to 2 atoms of oxygen, form titanium dioxide, or TiO. In white titanium pigments, titanium dioxide is at work wherever color is used to whiten or brighten our world, either outdoors or inside, covering surfaces, making materials like papers and plastics bright and opaque, and lending an air of lasting lightness to modern living. Yet, strangely enough, this whitest and brightest of all pigments comes from the blackest of ores. Ilmenite, which is one of the few titanium minerals from which titanium dioxide may be derived, is a combination of titanium and iron oxide that lends itself to pigment manufacture. In general, there are 2 types of these ilmenite deposits: those that occur in the sands of beaches and those embedded in massive rock formations. While deposits occur throughout the world, those of leading economic importance are located in New York State, Canada, in Florida, in Norway, and clear around on the other side of the globe in India. In sandy deposits where ilmenite is mixed with grains of sands, often bearing monazite, it is not so difficult to separate the ore from the sands, and that is why beaches were the first to be worked for making titanium pigments. In India, at Travancore, beach sands were gathered as early as 1911, before titanium pigments were known. Then, the monazite was needed to make chemicals for gas mantles. Today, the sands are transported as in the gaslight era, but now the ilmenite is recovered and concentrated. Waste is dumped back into the ocean, while the pure titanium ore is readied for shipment before the arrival of the monsoons. To go from the shores of Asia to the source of the Hudson River in New York's Adirondacks offers many sharp contrasts, including the type of ore deposits. In these mountains, locked between hard rock formations, ilmenite is found combined with magnetite or magnetic iron oxide. Here, a few miles south of Lake Placid, is the McIntyre Mine of National Lead Company, the largest producing titanium mine in the world. First discovered by white men in 1826, the ore was originally mined for iron, the titanium being considered a useless waste product. It was not until 1941, when the nation's defense effort needed a good domestic source of titanium ore, that this property was developed for its ilmenite, with the iron reduced to secondary importance. Collecting ore is a continual job of drilling, blasting, and breaking rock to sizes suitable for working by the forces of gravity, and especially magnetism. It is the shovel operator who takes the first steps in separating the ore from the waste, loading rocks of size suitable for the mill. The milling process is basically one of crushing and grinding, then of separating. First, the ore will be separated from the waste rock. Then the magnetite will be extracted, and gangue waste materials like feldspar, hornblende, and garnet rejected, until the remaining ilmenite is purified and concentrated. Each truck hauls 20 tons of rocks, about the size of a suitcase, for dumping down a chute. The load is held back by a curtain of chains before being fed into the hopper of the jaw crusher to be broken to the size of footballs. And then conveyed for further reduction to the cone crushers. Where the stony footballs will be broken to pieces the size of large marbles, and then to fragments less than ½ an inch across. After the fragments are screened, those that are too big are run over a magnetic pulley, which pulls the magnetic ore containing ilmenite, magnetite, and gangue out of the non-magnetic waste rock. For the next application of magnetic force, the ore must be pulverized in wet rod mills until it is as fine as grains of salt or pepper. The wet ground ore is pumped to a wet magnetic separator, where the magnetite is separated from the ilmenite. This is readily done because the iron mineral is the more magnetic, so that the titanium mineral is unaffected by the low-intensity magnetic separator. The waterborne magnetite particles are held to the underside of the belt by the magnetic field above. As the belt moves out of the field, the magnetite slurry spills off to be dried and made into lumps called sinter, used in the steel industry. To handle the enormous volume of ore, this operation must be carried on by a large battery of these magnetic separators. The remaining ore contains not only ilmenite, but also sandy or silicious waste materials. To separate them, the second force, gravity, is put to work. After being divided into different sizes, the material is refined and concentrated on these reciprocating tables. The operation is based on the fact that grains containing ilmenite are heavier than grains of waste materials. As the tabletop slowly moves forward and then quickly jerks back, the heavier ilmenite gathers behind the riffles, while the lighter waste is washed off and over the side. In this way, the different sizes of almost pure ilmenite are discharged in concentrated form off the end of the tables and sent to filter wheels, where the water is sucked out through the fabric covering. The semi-dry ilmenite is conveyed to a bin where it is dried by steam coils until it becomes a free-flowing product that can be more easily refined by high-intensity magnetism. First, to be sure the ilmenite is shipped as the purest practical concentrate, it is passed through a low-intensity magnetic separator to remove any remaining magnetite. The small belt passes under the electromagnet and at right angles to the broader feed belt, from which it picks up the magnetite. The feed then passes under a high-intensity magnet that separates the ilmenite from traces of waste materials. The small belt passing under the electromagnet and at right angles to the broader feed belt from which ilmenite is picked up. At last, ore that was once locked in stone, solid as the rock of ages, is now set free as concentrated ilmenite, ready for shipment to plants in St. Louis, Missouri, and Sayreville, New Jersey, where this shiny black powder is transformed into a dozen grades of the most brilliantly white of all pigments. The titanium ore is shipped from the source of the Hudson to the 2 titanium pigment plants of National Lead Company. This one on the Mississippi River at St. Louis, and this one on the Raritan River at Sayreville, New Jersey, reveal how the ore comes in black, and after conversion, the finished pigments are shipped out white. Take it black and make it white, the strongest possible white. That is easily and quickly said, but it requires quite a bit of doing and lots of space. The fact that the final product combines the highest quality with the utmost economy is attained through the world's largest volume output of titanium pigments. For example, it takes the highest grade ilmenite ores, tons upon tons of them, not only from the Adirondacks, but from mines in more distant places, like those in Norway and India, countries that regularly send ships to this unloading dock. Then it takes power from the plant's own generators, as much electricity as is required to light the streets of a city about the size of Chicago, and water, pumped and purified. As many gallons are used from the mining of ore to turning it into pigment as are consumed by cities the size of St. Paul, Minnesota, or Fort Worth, Texas. Sulfur is needed, and first it has to be turned into sulfuric acid by the contact process in the plant's own manufacturing units. And limestone, the purest obtainable, to be turned into calcium sulfate at the St. Louis plant in the manufacture of composite titanium pigments, composed of titanium dioxide and calcium sulfate. Although these are the basic materials for making titanium pigments, there are also others, including, of all things, scrap iron. As will be shown later, it is used not as a metal, but as a chemical, a reducing agent. With all such channels of supplies in operation, the actual manufacturing process can be kept running around the clock and throughout the year. Like furnaces for steel making, titanium pigment equipment cannot be allowed to grow cold. To keep it going takes the most important element of all, the human element. The efforts of hundreds upon hundreds of employees, bricklayers and chemists, engineers and electricians, lead burners and bookkeepers, to name a few of the 80 different skills it takes to make titanium pigments. Around the clock, at every stage of production, constant control, sampling, testing must be maintained. Every shipment of raw material or finished pigment must be analyzed and its quality certified. In a single plant, routine supervision requires over 2,500 analytical controls every day, over 100 an hour. Regardless of the vast scale of these operations, all variables, such as temperatures, concentrations, rates of flow, are as rigorously regulated as in the most critical laboratory experiment, and are held within extremely close limits. But here, in what has been called the world's largest operation of a complex chemical process, reactions take place inside tanks and other equipment that conceal them from the eye. However, when actual production scenes like these are combined with a master chart outlining the 5 major processing steps, and also with simplified laboratory demonstrations of the chemical changes, it is easy to follow processes that might otherwise be completely obscure. First, the ilmenite ore is added to strong sulfuric acid to form a suitable titanium solution. This single step requires several operations. The incoming ilmenite must be dried and ground to required fineness. Then, as this laboratory demonstration shows, a weighed amount is added in specified proportions to a measured quantity of very strong sulfuric acid. The addition of water dilutes the acid, causing heat to be given off, raising the temperature, and starting the reaction between ore and acid that gives off a tremendous amount of heat. When the reaction is complete, the mass is dissolved with water. At this time, a small amount of scrap iron is added to reduce chemically the iron in solution and so prevent it from oxidizing and becoming a source of contamination. In actual production, in a tank over 17,000 times the size of the laboratory glass beaker, it takes 15 hours for the maximum amount of ore to be dissolved. And this is only one tank in the battery of similar tanks that must be used and staggered for continuous volume production. Throughout, the specific gravity, acid strength, and temperatures must be regulated, and the solution analyzed to note what is happening to the titanium, iron, and sulfuric acid. The digestion process leaves the solution with a suspension of muddy residue. The solution is then clarified by settling out the insoluble ore which sinks to the bottom of the tank. This residue is washed for maximum recovery of the solution. The clear solution overflows from the settling tanks and is then filtered to remove any further traces of insoluble ore. To obtain the correct strength and proportions of iron sulfate, sulfuric acid, and titanium, the hot solution is pumped to a vacuum evaporator, seen here as a flask, where the reduction of pressure causes it to boil. As it cools, due to the rapid evaporation of water, part of the iron crystallizes as iron sulfate or copperas. The green crystals of iron sulfate are removed by filtering. The process demonstrated here in the laboratory differs only in magnitude when carried out on the scale necessary for efficient production. A byproduct, this green copperas is sold to water treatment plants and iron pigment manufacturers. The titanium solution itself must be further concentrated in a vacuum evaporator, where temperatures and proportions are rigorously controlled to prepare the liquor for the second and most dramatic step, boiling the solution to give a suitable precipitate of titanium hydrate through hydrolysis. In short, turning black to white. A measured amount of solution, heated to the proper temperature, is fed at a controlled rate into the right proportion of water regulated to meet temperature and purity requirements. Immediately, a white, cloudy precipitate forms of nuclei or seeds. Although seeming to disappear, they are extremely minute growth centers, which accelerate further precipitation. During boiling for hour after hour, the titanium sulfate in water is decomposed by hydrolysis to produce titanium hydrate, which is titanium dioxide containing water and some sulfuric acid, a precipitate composed of extremely minute particles that must be of the right size and purity for pigment production. It is at this precipitation stage that the making of composite pigments differs essentially from pure titanium dioxide in that precipitation takes place in the presence of calcium sulfate, formed by the addition of a water slurry of the highest grade of limestone to sulfuric acid. The calcium sulfate produced is of the proper particle size, purity, and surface, because the strictest controls are kept upon such crucial factors as dilution, rates of flow, temperature, and acid concentration. The titanium solution is added to this calcium sulfate along with nuclei just before hydrolysis, so that the titanium hydrate precipitates and is deposited upon the calcium sulfate, forming a tight union of these substances, a truly coalesced composite pigment. This fact is established by the electron microscope, which magnifies the pigment particles on a scale comparable to enlarging a housefly to the size of the tallest building in the world. On this electron micrograph of particles of the composite pigment, a special technique reveals that the titanium dioxide is attached to the calcium sulfate. On the vast scale required for continuous volume production, it takes several hours for the white of titanium hydrate to be fully precipitated from the dark solution. Throughout, samples are taken and sent to the control laboratory to check the progress of the precipitations from a large battery of tanks. Whether of the composite type or pure, the titanium hydrate is next separated through filtering, purified by washing, and conditioned chemically. A leaf filter is used to remove the white titanium hydrate from what is now the spent mother liquor. In comparison with this laboratory equipment is the vast array of vacuum filters, an indication of the scale of equipment required for efficient quantity production. Because there are still traces of iron and other impurities which affect pigment qualities, the filter cake is continuously washed. The washed cake or pulp of titanium hydrate consists essentially of titanium dioxide and water. To decrease traces of any remaining impurities to a harmless level, the hydrate is specially treated with conditioning agents that also ensure the development of proper particle size, crystal structure, and maximum whiteness and brightness. Now, the titanium hydrate is ready to be subjected to the intense heat treatment termed calcination to be converted to titanium dioxide. After the conditioned pulp has been dewatered through filters, the cake is fed to the calciners, long, slowly rotating kilns or tubular furnaces, heated by oil or gas at one end. Here, the intense heat evaporates the water and stabilizes such pigment properties as tinting strength, color, and resistance to chalking. The particle size develops until titanium dioxide emerges, but is still not ready for pigment use because the heat has caused it to form into lumps. The crux of this process lies in the exact control of such variables as temperature, heating, and feed rates. The final step takes the titanium dioxide through milling and further conditioning to produce finished titanium pigment. Because this involves wet milling and surface treatments, further filtration and drying are necessary. The type of milling varies according to the type of pigment produced. Frequently, various combinations of grinding are needed. For grades like the unique titanium calcium pigment and water-dispersible titanium dioxide, dry pulverizing through ring roll mills equipped with air classifiers and high-speed hammer mills ensure the correct texture and fineness, while other grades require wet milling. After the pigment is suspended in water, dispersing agents are added to the slurry before it is ground in pebble mills in a closed circuit with centrifugal classifiers, which return oversized particles for further grinding while sending on the finer sizes for surface treatment. Because only the surfaces of pigment contact other materials, like the vehicle of a paint film, and 1 pound of pigment particles has about an acre of surface, each granule must undergo a skin treatment for such properties as ease of blending in paints and plastics, resistance to chalking, and reduction of after yellowing in enamels. With the treatments fixed, the pulp is filtered, then dried, then super pulverized. For some types, including the composite pigments, this is done by fluid energy mills in which high pressure steam passes through jets to swirl the pigment aggregates upon themselves at tremendous speed until they disintegrate. The final product consists of ultimate particles half the wavelength of light. so small they can be seen only under an electron microscope. All production is scientifically sampled. Before it is finally approved, it is analyzed chemically and tested for all pigment qualities. For example, ease of mixing with paint vehicles, freedom from coarse particles, high gloss producing power, and uniformity of high tinting power, the unsurpassed ability of titanium pigment to lighten dark colors. Even after the pigment has been approved for uniformity and excellence, and it is bagged for shipment, research still goes on in places like this outdoor paint testing laboratory at Sayville, Long Island. In a location selected for climatic conditions of sunshine, humidity, and temperature variations, there are 2 miles of surface area devoted to continuous testing of titanium pigments in exterior finishes, using all kinds of vehicles for all kinds of surfaces: wood, steel, asbestos, cement, brick. These rows upon rows of test panels form streets, two-way streets, where ideas and results are exchanged with paint manufacturers. This is the birthplace of such developments in exterior paints as the first titanium pigmented paint, the first chalk-resistant titanium pigment, the 2-coat paint system, and the truly 1-coat paint. Here, solutions are continually found to many paint problems. For example, chalking. How to hasten it under controlled conditions so white house paints will shed dirt and stay clean. How to delay it with chalk-resistant titanium pigments for lasting tints in finishes not only for wood but also metal. Or how to check cracking and scaling so as to prolong durability through skillful balance of pigment and vehicle. Or to prevent the staining caused by screens and building hardware by using titanium pigment as the sole pigment in the paint formula. All findings are made available to the entire paint industry. The finishes evaluated for weather resistance on these fences often come from work conducted as a service to customers in laboratories centrally located in New York City. It is here that research is conducted on the use of titanium pigments, not only in paints, but also in paper, rubber, plastics, porcelain enamels, and many other products. Paint studies are concerned with such basic benefits from titanium pigments as hiding power, as well as with properties which are the result of a correct balance of ingredients. For example, consistency and cleanability. Sometimes, in accordance with a manufacturer's ideas or independently, developments lead to improved formulas or new types of paints. Similarly, in rubber and plastics, the values of titanium pigments to brighten, whiten, and make opaque without affecting strength are the subjects of continual development. Special types of titanium dioxide have been developed for porcelain enamels, and studies are always underway in ceramic products to test the outstanding qualities of titanium porcelain enamels. Because of the pigment's exceptional hiding power, the coatings are thinner than earlier enamels and also are far less brittle. In paper, work is continually in progress on the value of titanium pigments for increasing whiteness, brightness, and opacity, especially in coatings, so that printing is clear and bold on one side of a page without showing through onto the reverse. To help solve these and many other problems in the end uses of titanium pigments requires knowledge gathered from experience with product applications, along with information gained from fundamental studies carried on at the Research and Development Laboratories at Sayreville and St. Louis, where work is directed toward both improving present pigments and discovering new ones. Titanium dioxide crystal structures are studied through X-ray spectrometry. Not only the size and shape of pigment particles are determined by the electron microscope, but their surface area is measured through gas adsorption. Reflectance, whiteness, and color are studied by the most precise photometry. Trace elements that influence these properties are determined spectrographically. Even radioisotopes are employed in tracer techniques in the study of processes for making titanium pigments. As for the results of all this research, well, to put it bluntly, they are sometimes nothing short of astounding. For example, in order to learn more about the surface and about the transmission and reflection of light by rutile titanium dioxide, it was helpful to build a large transparent crystal which could be more readily handled and observed than the minute particles of pigment. It was interesting to learn if the crystal showed any color. But when the crystals were grown and cut and polished, they proved to be gems of incredible beauty, whose brilliance is a result of the high refractive index, which governs the ability of minute pigment particles to reflect so much light that they give highest hiding power. Titanium dioxide can be formed not only into gems, but transformed into a metal stronger than aluminum, yet more resistant to rust and corrosion. While about only half as heavy as steel. First used mainly for jet airplanes because of its strength at high temperatures, titanium metal is another example of how new materials grow out of research into new ideas. One produces the other. And it is the combination of both that has helped create our brightly colored modern world out of the dingy shades of former times. Less than half a century ago, colors for homes were drab, just as the only stable color for cars was black, which explains why the Model T Ford came in that color. But today, it is the magic of titanium pigments, not only in paints, enamels, and lacquers, but also in paper and in rubber, in all the forms of plastics, in leather goods, in synthetic fibers for textile products. In every type of floor covering, and in granules for roofing. It is titanium pigment that has helped create the beauty and brightness of our world, so that no matter where we look, as far as the eye can see, there, silently at work, is this magical ninth element in the form of titanium pigment, so white, so bright, so opaque, that the very colors on this motion picture screen acquire their vividness from the reflecting power of its surface, which depends for its brilliant whiteness upon titanium pigment. Named after the Titans, the giants of mythology, it has become the modern giant from black earth that man has tamed to turn his world lastingly white, lastingly bright,